Hello, I am Rasmus Benestad, and I will present some work connected to how we derive regional climate information that can be useful for climate change adaptation and also study the resilience to climate change. And this work that I will present was done through a project or an EU project called EU Circle, which was a pan-European framework for strengthening critical infrastructure resilience to climate change that also involved Bangladesh. And we wanted to study the effect of tropical cyclones and the resilience to those in the city of Kulnha in Bangladesh. The tropical cyclones are also called typhoons in that area of or that region of the world. So the traditional approach would be to apply what we call downscaling to simulate with regional climate models with high spatial resolution the weather in that region. But it would be difficult to find good specimen of tropical cyclones because they are rare in the real world, and also there are few simulations and many of them don't have the high resolution that we need. So that would imply a long search for imperfect replicas or digital replicas. So the question was then, are there other types of approaches that might be useful for our study? So it turns out there are three different approaches that we can derive information on regional climates and resilience. And these are shown here. So the first one that we chose was stress testing and synthetic storms, which I will explain a little bit later, that we actually adopted for this study. And then another approach would be sensitivity tests, which addresses the question, what is the most important aspect of climate change? What are the key elements that really affects us? And then I will also discuss the traditional way that downscaling and how to provide the best description of the regional climate outlooks. So this slide here shows the publication describing stress testing for climate impacts with synthetic storms. I would say it's a bit, well, I would call it non-scientific. It's more like an engineering approach, and it's very practical. And it involves looking at the archive of past weather forecasts and pick events that we already know about that made an impact and use these as analogs for Bangladesh. And this, of course, requires some impacts models that will simulate the flooding or the wind stress, so we can use these to assess the resilience in this study. So we choose data from climate services. In this case, we picked some old weather forecasts, but you can also take some reanalysis from the Copernicus C3S climate service, and these you can download for free. And you can, and then we took the case of Hurricane Matthew that hit Haiti in 2016, and we applied. We took the wind fields from this event. Here's Kulnha here. So you can see the winds blowing here, and also the rainfall associated with this event, and moved it to Kulnha to see what happened. So this is an analog for the worst case scenario, and it provides a stress test for wind and rainfall in this case, if we have an impact model that can take these as inputs. And we use then weather forecasts for historical events. And this slide shows the situation here. Here we have the original Hurricane Matthew hitting Haiti, And here it was moved over to Bangladesh. So just moved, we changed the coordinates of this hurricane and also the times of it as well. And here you see a blown up description of the hurricane. We picked the Hurricane Matthew because it arrived from the south, so it came from the sea, and that's similar to in Bangladesh. So it would come from the sea and hit land, and the sea is fairly similar in different parts of the world. So there are some similarities in these two cases. Another approach is sensitivity testing, and we can apply this approach if we have some models for instance, runoff or agriculture or economy, and then we ask the question, what are the most important aspects of climate for me? And then you can use these models and feed them with observations that we have of temperature and rainfall. And we can do that many times, and each time we do it, we may say, remove some rainy days, add some rainy days to sort of simulate more or less rainfall or droughts. But also we can add, we can increase the temperature or reduce the temperature to simulate what happens when the temperature changes as well. Or we can also use weather models, weather generators as input as well. So this example shows a case for the maize fields in Tanzania, where the results are based on a DSAT CSM, and it was Habiba Montgomery who did this study, and you can see here she changed the rainfall intensity and then looked at how that affected the crop yields. And also she did the same thing for temperature, which is shown here. And you can see that there was a stronger effect on temperature. So there's by increasing the temperature by about 1 degree, then she increased the crop yields, and then after that, the crop yields decreased after that. So these are 4 different places in Tanzania. And then the traditional approach is downscaling. So the problem is that we measure the rainfall, for instance, or in these rain gauges here, and we want to know how much water these buckets collect. Whereas the global climate models that we have a very crude representation of the world. So that each grid box is by 100 kilometers typically. So how can we then make use of that information and say something about what falls into this bucket, or how the temperature at this location changes? But fortunately, what we are really looking for is the change in the statistics of rainfall and also temperature. So when it comes to rainfall statistics, we can see that from a global state, this is a global mean rainfall, that there are certain patterns. So there's more rains in a band around the equator, and also more rains in the storm tracks here. So here's the band around the equator. So the rainfall is systematically influenced by the geography, and also the statistics is predictable, and that is very useful for downscaling. There are 2 different ways of downscaling. One is called dynamical downscaling, and the other is called empirical-statistical downscaling. So the dynamical downscaling involves regional climate models, which look a little bit like the global climate models, but are made for a limited area and have higher resolution, spatial resolution. I will actually address more the statistical type here, because we want to say something about how the statistics change in the future. So here's a typical. You can represent the temperature by a normal distribution where you have the mean and also the standard deviation, and the climate change will imply that maybe the mean changes. So then you have like the gray curve becomes the red curve, the red curve here, or maybe the standard deviation changes as well. So that's this figure here shows how like what a climate change would look like in terms of temperature. Also, the same thing we have for rainfall or precipitation. The main difference between precipitation and temperature is that temperature you have all the time. You don't have any time when you don't have temperature, whereas when it comes to precipitation, sometimes it rains, sometimes it doesn't. So then we have to distinguish between the two, and we divide the days into rainy days and non-rainy days. And for the dry days, basically there's no rainfall, so that's easy. There's just zeros. And then we just look at the rainy days, and then we see that the statistical distribution is like a bit like this, because we don't have negative rainfall. And again, if we use this exponential distribution, we only need one parameter to describe its shape, and that's mu here, and it can change, and then you can get a climate change here, wet mu here, and so it slides out, and you get more heavy rainfall events. So the x-axis is the amount, and the y-axis is how often does it happen. The same thing here as well. But for the rainfall, you have two parameters still, because you need to say something about wet day frequency as well as the mu here as well. And again, both of these have predictable patterns, so they are predictable and also fairly robust, and they are very useful for decision making. So here's one example, which is where I show temperature, but I also could show precipitation, where we show statistical properties that we have graded and made a map from empirical-statistical downscaling, ESD here. And in this case, these results represent 151 runs from 1951 to 2050. And this figure shows the 95th percentile of the winter temperature projected for 2050. That's a CMIP 6, so that's the latest batch of global climate models. But it's important to not just use the statistical downscaling. You need to show both statistical and dynamical downscaling in order to get robust results, because they have different strengths and weaknesses, and sometimes they might be wrong. So we need to combine the dynamical with empirical statistical downscaling, and this is what is shown here. So the blue ones are the dynamical downscaled results, and the red curves are the statistical downscaled results for the same models as the blue ones. But because the dynamical downscaling requires a lot of computational resources, we can't apply them to many global climate models, but we can do that with statistical downscaling because it's very cheap computational wise. So if you do it for the statistical downscaling on all global climate models, then we see that we get a much better, a larger spread than if you just take a smaller selection. But we see that the statistical and dynamical downscaling seem to agree quite well. And we can apply also statistical downscaling to downscale other types of statistics. So if we have the wet day mean precipitation and the wet day frequency, then we can use this formula here to estimate how the intensity, duration, and frequency curves change. And this is basically, this shows like the duration of rainfall in terms of hours. So here's up to 1 day here, and the return level here on the y-axis. So and then you have different return periods here with different colors. So this is a 100-year event, and this is a 2-year event. So that's very useful for climate change adaptation. It is also important to stress that we need to look at the past observations as well, the historical observation, and look at what trends there are and what they look like as well when we do the downscaling. and not the least, we need to use this to evaluate our downscale results. So this approach on the downscaling is presented in a discussion paper here, a Norwegian approach to downscaling, and here you also have the QR code and also the website. So that's in GMD discussion here. Before we finish, I would also like to say that it's important that climate change adaptation is based on robust regional climate information, based on the calculations and the best data that we have, and the science, the climate science as well. Sometimes we get the impression that the climate change adaptation is not based on science, but is more based on goodwill. So that's it. Thank you for your attention. And this is also work that I've done together with my colleagues, Abdulkader Mesghani and Kaisa Parding.